In this video, we are going to start doing some binary arithmetic. In particular, we're going to do addition, we'll do subtraction, and we'll do multiplication. But we're going to hold off on division for another video because division has caveats depending on whether you're using signed numbers or not. And that sort of implies the benefit of the other three, and that's that with addition, subtraction, and multiplication, the core mechanics work the same way regardless of whether you have whether you're treating your storage for your numeric values as signed or unsigned values. And so they're very easy to learn. Now the first thing we have to do is settle on a size, and so I'm just going to pick 8 bits because it's relatively small but big enough for some fun operations. And it's really arbitrary for the sake of example. Now let's do addition first, because addition is one of the most repeated operations inside of a CPU. We do addition like all the time. For for loops, we're adding one, and in some situations, of course, with loops, we're decrementing one. But that's subtraction, and subtraction is really addition of a negative number. And so to do subtraction, we need to do addition. So addition is double duty there. Now, multiplication is really iterative addition, and so we're using addition again. And division, more or less is iterative subtraction, which is addition of a negative number. So it's very important that we have the basic mechanics of addition down. Let's pick some values here. 0, 1, 0, 1, 1, 0, 0, 1. That's a good value. And we'll add to this 0, 0, 0, 1, 1, 1, 0, 1. All right, that seems relatively reasonable. Now, just like addition and decimal, we're going to start with these lower order digits and then work our way this way. And if we get a result that's too big for one digit, we'll carry the remaining digits across one or more of our other positions. Now, if we're only adding 2 binary numbers together, at most we'll have a carry of 1. Now, we could carry nothing, but we won't get a carry larger than 1. If we were doing something like multiplication, where we have lots of partial sums added together, we might effectively on paper have to add 3 or 4 or more numbers together, in which case we could have a carry that's larger. For example, if we were to come up with a partial sum in a column of the number 4, we'd have to put a 0, carry the 0, and a 1. And that's just because it's the bit pattern for 4. We won't see that in addition of 2 numbers, though, so we can do this pretty straightforward. 1 plus 1 is 2, so that's the same as a 0 carry the 1, because 1, 0 is 2 in binary. 1 and 0s are 1. 0 and 1 is 1. 2 1s is 2, so that's 0 carry the 1. Now here's 3 1s, so that's the bit pattern 1 1, but you can think of it as 1 carry the 1 if you prefer. But it's really just the number 3. All right, 1 down here in zeros, that's a 1. 1 plus 0 is 1, and 0 plus 0 is 0. And ta-da, we've done it. So that's our basic addition there. I'm going to do it real quick. Let's do the conversions to see that our work is correct. So if we look at this one is the bit pattern for 89, and this one is the bit pattern for 29. Yes, 29. And that means we should have come up with a sum of 118, right? Let me double check. This is the one. No, this is the 64. Yes, 118. Looks good to me. So let's do addition one more time. Up here, get a little more practice in. What about 0, 1, 0, 0, 1, 1, 0, 0. We can add to that 0, 1, 1, 1, 1, 1, 1. I'll put a 0 here at the end. Right. Now what I'm trying to do here, although I guess I really only needed the 2 ones in this position, is to force us into a circumstance where the result of this is so large that the high order bit becomes set. And that's just to remind us that if we're doing unsigned numbers or signed numbers, that high order bit is actually meaningful outside of a coefficient for a position. This is the signed bit if it's a signed situation. But the mechanics don't care. So we just add these up. 0, 1. 1 plus 1 is 0, carry the 1. 1, 1, 1 is 3, so that's 1, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And 3 ones is 1, carry the 1. And 1. All right. Now our interpretation of this will have to differ in the 2 possible ways. Over here, whether it was signed or unsigned, because the signed bit position is a 0, we would have in both cases said either 118 or positive 118. Over here, this is our 64 and our 8 and 4 bits, so this is 76. And down here, we've got, this is 126. Yeah. All right. So let's see what we got when we add these together. This is the 128-bit, 64, and 10. So that is 202. Which, let me double check. 12, 1. Yeah, that's what we should come up with. 202. That's if this is unsigned. This would just be treated all as a magnitude. Now, if this were a signed situation, we'd have to treat this as a negative number. So to figure out what it means, we would have to negate it. So we know this is going to be negative, but we need to negate this by flipping all the bits. There we go. 1, 2, 3, 4, 5, 6, 7. Yep, counted them right. And then adding 1 to that. And that will give us the bit pattern 0, 0, 1, 1, 0, 1, 1, 0, which is 54. So this was a negative, this original bit pattern was a negative 54. Now, this may seem peculiar. So here we are adding 2 positive numbers together, and if we treat them as signed values, we end up with a negative. So positive plus positive in general should not equal negative. Now, because that is an unexpected sign change, we would say that an event called overflow has happened. And the same thing could happen if we subtract too far and we go from a very low negative number suddenly to a positive number. That's also overflow, although very often people will call that underflow. But it's the same effective phenomenon. We have torally wrapped around our representational space. Now, we have to feel comfortable, though, that negative 54 is right. It's easy to see that 202 is right, but negative 54 seems a little bit weird. So let's break that down briefly. We have 126 here, to which we were adding 76. Now, we've got 8 bits of representation, which means we have 256 different bit patterns. If we got rid of the top bit, the sign bit, and said we'll just put a 0 there because it's going to be a positive number, then we're left with 7 bits, and that gives us 128 different values, but one of them is all zeros, which means the highest that we can get from a 7-bit value is going to be 127. Now, if we treat this back again as 8 bits and we think about the highest positive value, there'd be a 0 here and all ones, which we just figured out would be 127. So to get from 126 to 127, we add 1. That's sort of obvious because there's only that one bit missing. So I'll add 1, and that's really taking 1 away from the 76 that I'm going to add. So after doing this, I'll still need to add 75 more. So let's see, 126 plus 1, that gives us 127, the largest positive number we can represent with an 8-bit 2's complement representation. So what happens when I add 1 again? Well, it's going to wrap around to the lowest number that we can represent. Remember that in sign magnitude in 1's complement, we had mirrors on the range. So if we went up to positive 127, we would go down to negative 127. But with 2's complement, we could go down 1 deeper because we slid the bottom half of our chart down to get rid of the duplicate zeros, which means we can go to negative 128. So if I now take 127 and add 1 more from our original 76, which has happened twice, so we'd be left with 74 to add, that's actually going to give me negative 128. So I have 74 more to go, and if I take negative 128 and I add to that 74, there's the 4, we get negative 54, which is what we came up with over here. So you see, even with the signed interpretation, the mechanics give us the correct result. All right, I want to do one more addition before we move on to subtraction. And this one is going to be real simple. Let's just do a 1 in the high bit and then a bunch of zeros. So there's an 8-bit number, and I'm going to do the same bit pattern. Down here, and we'll add these together. And really my purpose here is now to force, take two numbers where the signed bit or the high order bit, depending on whether you're signed or unsigned, had ones, and then getting them to sort of disappear. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 1 plus 1 is 0. Carry the 1. That gets us a 1 here. But since we are working off of an 8-bit system, this guy here is gone to the bit bucket, which means whatever this value is plus whatever this value is going to get us the number positive 0. And that number is interpreted the same way regardless of whether this is a signed or an unsigned system. Now, we would like to know what these values represent, but since they have ones in the sign bit, unlike our other two examples, the interpretation depends on whether we are in an unsigned representation or a 2's comp representation. So if we are unsigned, then this is going to be 128. And since they're both the same bit pattern, they're both 128. Now if this were 2's complement, then this is a negative value. They both are because they're the same. And to find the result, or the equivalent of this, so we know it's negative, we'll flip all the bits, so 0, 1, 2, 3, 1, 2, 3, 4, and then we'll add 1 to it. And this, of course, gives us one of the anomalies that we've seen before in our sign or in our 2's complement representation, because this is going to be a 0, carry the 1. 0, carry the 1. And this carry is going to ripple all the way down to here. And so we get the same bit pattern that we started with. But that doesn't mean we have to say, oh, now this is negative. Remember, we're just converting from here to some absolute unsigned value for the purpose of printing out in the human world what this means. And then this becomes the number 128, which means the original value was negative 128. So in unsigned land, if we take 128 and add 128 to it, we're going to end up with positive 0. But if we wrote down all the bit patterns in 8 bits, starting with all zeros at the top and all ones at the bottom, and we went from all zeros, or we found 128, which would be down at the bottom. And then tried to do the addition of 128 all again, we would find ourselves ending up back on 0. Now, a similar thing would happen with us over here. We would just discover that negative 128 minus 128, or plus negative 128, is also going to give us positive 0. But we don't have to worry about those caveats because they aren't even caveats. The mechanics are always the same for addition, whether it's signed or unsigned. So the point of all this is just to show you the mechanics and just to say, mindlessly do it. Be the computer, be a mindless automaton, and everything is going to work itself out just fine. All right, let's do some subtraction. Now that we've gotten through the worst of this, subtraction. And again, we're going to be doing 8 bits. Right? And once again, subtraction is really the same as adding a negative number. And so we will have to use a signed representation to hold the negative number. But we're just doing that mechanically. It doesn't matter whether the actual values we are dealing with are supposed to be interpreted as unsigned or as signed. It will still just work out. So, because it's just addition. So let's say we take those same values we had before, 0, 1, 0, 1, 1, 0, 0, 1, and then we subtract from that 0, 0, 0, 1, 1, 1, 0, 1, right? That was our 89 and our 29. So we're doing 89 minus 29 effectively. Now we know what the result of 89 minus 29 is going to be. That's easy. That's going to be a positive 60. But we need to do this in binary. So the first thing is we got to convert this subtraction to addition, which means we need to find the negative of this bit pattern. So let's convert this. That will mean flipping all the bits, 1, 1, 1, 0, 0, 0, 1, 0, and then adding 1 to that, which is going to give us 1, 1, 1, 0, 0, 0, 1, 1. So this bit pattern is equal to negative 29. So now we can add negative 29 to our original 89. 0, 1, 0, 1, 1, 0, 0, 1. And we'll add to that this, 1, 1, 1, 0, 0, 0, 1, 1. Now notice this said negative, so I just flipped all the bits and then added 1. I didn't actually care whether this was positive or negative at all. If this was a negative, if this would have had a 1 in the signed bit, of course could be unsigned number, I wouldn't care. I would see the negative and I'd flip all the bits and add 1 and then just go with it, because such is the nature of binary arithmetic. So now I'm going to get a 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus nothing, 1 plus nothing, 1 plus nothing, 1 plus nothing. 1 plus 1 is 2, so that's a 0, carry the 1. And 1 plus 1 is 2, so that's a 0, carry the 1. And we get this 1 here, but because we're on an 8-bit system, this guy, he goes to the bit bucket, as we have seen before. And then the question is this number equal to positive 60? We certainly hope so if it's 89 minus 29. So let's figure out what we got here. This is, what do we got here? 1, 2, 4, 8. So that's 12 plus 16 plus 32. Sure enough, it's 60. All right. Now, so subtraction is just multiplication. You just start by first negating the second value. So whenever you see A minus B, don't worry about whether B appears to be signed or unsigned, or have a 1 in the signed bit. Just negate it with a 2's complement representation so that you can do A plus negative B, and everything will be fine. All right. Multiplication. Multiplication. Again, we are looking at an 8-bit system. Now with multiplication, since the numbers get big quick, we'll do an initial example with some smaller numbers. But in order to do multiplication, we'll have to remember when you do decimal multiplication, you have all these individual positions, and then you take the lowest order digit in the bottom value multiplied by the lowest order in the top, and then the lowest one by the next highest, or the next lowest in the top, and so on over. And to do that, we had to memorize in grade school this multiplication table. I hope you remember it. It had in one edge the values 0 all the way up to 10. At least that's typically what we had to do. But for the sake of doing it with digits, we could just pretend it goes from 0 all the way up to 9. Down the other dimension were also the other coefficients in decimal, 0 all the way down to 9. So we had a 10 by 10 grid, meaning it had 100 elements in it, and we just had to memorize those things. Now the good thing was there was that sheer line across the diagonal, and the whole thing was just a mirror image of itself. So you really only had to remember about half of it. And we're going to unfortunately have to do the same thing for a binary so that we can do multiplication here. The good news is that the binary multiplication table is about this big, because in one dimension our coefficients can be 0 or 1, and in the other dimension they could be 0 or 1. So multiplication in binary will turn out to be very nice because we only have to remember 4 things. And realistically, 0 times 0 or 0 times 1 is going to be 0. 0 times anything is 0. So everything in this column is 0. Everything in this row, because it's multiplied by 0, is also going to be 0. So the only actual cell we have to remember is when 1 is multiplied by 1, which of course gives us 1. Phenomenally simple, right? So let us do some multiplication. I'm going to start with numbers and then figure out the bit patterns. Let's do 12 times 10, because that will give us 120, which is still going to be positive whether we interpret it as signed or unsigned. So I'm going to do 10 times 12, and I should get 120. Let's get the bit patterns for this in place. For 12 and 8 bits, we've got 1, 2, 3. The high nibble is all empty, and then we'll have 8 and 4, and 2 zeros there. For 10, 0, 0, 0, 0, 8, and 2. All right. Let's do the multiplication. So to do the multiplication, it's just like you do it in decimal. We're going to take 0 and multiply it by this 0, and then 0 times this 0, and then 0 by this 1, and 0 by this 1, and so on, and write the results in each consecutive column. However, 0 times 0, we can check the multiplication table over here. It's 0. So that means there would be a 0 here and a 0 here. But 0 times 1, also check the multiplication table, also 0. So 0 times this whole bit pattern is just going to be 0. That means when the bottom value that we're using in our multiplication, the multiplier, when it has a 0 in its column, we're just going to skip that one, because it's not going to come up with a new partial sum that's anything other than 0. So adding 0 in our partial sums is dumb. It's a waste of our time. So we're only going to focus on the bits in the multiplier, the bottom number, that have a 1 in them. So here is a 1. So now we're going to multiply 1 times 0. But remember, because this is shifted over one position, we're going to put the result here, directly under this 1. So 1 times 0, well, if you recall, that's 0, because 0 times anything is 0. Well, 1 times 0 again, well, that's 0. 1 times 1, hey, that's our magic cell. 1 times 1 is 1. 1 times this 1 is 1. And then 1 times, well, all of these zeros will be zeros. And so I could write all the zeros down, but since there's no other 1s up here, I effectively have the quantity already. But notice something. If you pretend the other 4 zeros are here, then we would have 4 zeros, 2 ones, and 2 zeros. And the original multiplicand, the top number, is 4 zeros, 2 ones, and 2 zeros. So really, when you take this number and you multiply it by 1, you're just copying this bit pattern down here. I'm only saving myself the trouble of writing all those extra zeros that don't do anything. But that's really all we have to do in multiplication. So we're going to find the next one in the multiplier, and then I'm just going to write this bit pattern from left to right of the multiplicand down here, right underneath the 1 in question. 0, 0, 1, 1, and then 4 zeros that I don't care about. And because I'm through with the multipliers ones, I'm through with the partial sums, and I can add them up. So this column really did have a 0 in it, so I get 0, 0, 0, 1, 1, 1, 1, and then the highest order bit will get a 0. And then if we were to check that out, we would find out that this is the bit pattern for 120. And it's positive because the signed bit is a 0. And if it's unsigned, then it's just, well, 120 anyway. And so we've got it worked out pretty well. Now let's say we want to take some of those bigger bit patterns that we had before. I chose 2 small numbers so that we would get a number that fits in 8 bits. But I'm not going to do that now. I'm just going to use some of our bigger numbers from before. Let's do the 29 and 89 that we had before. So 29 is 0, 0, 0, 1, 1, 1, 0, 1. That's 29. And 89 is 0, 1, 0, 1, 1, 0, 0, 1. Yes, I think so. And we're going to multiply those together. Right. Now, I'm not going to pretend to do in my head what the multiplication of this is, but whatever it is, it's definitely going to be too big for 8 bits. And so multiplication puts us in a special circumstance. And a lot of, or I should say most computer architectures, the machine instructions that perform the multiplication actually give us a result that's twice as big as the core storage we were already using. So if we had an 8-bit pair of numbers, a pair of 8-bit numbers I should say, and we multiplied them together, the result is likely to be stored in a 16-bit register. However, at some point you just run out of storage places that are big enough, and so there will be truncation. So overflow can happen a lot easier with multiplication for obvious reasons, because it's like doing addition over and over and over again. Well, let's go ahead and do this using the method we used up there. We just look for ones in the bottom number, and then we copy the bit pattern on top directly under that number. So 1, 0, 1, 1, 1 is the bit pattern from low order bit to high order bit, excluding the upper zeros. So I can just write that under this one here. 1, 0, 1, 1, 1. Here's another one. 1, 0, 1, 1, 1. Here's another one. That's 1, 0, 1, 1, 1. Now I can already see this one is outside of the realm of my 8-bit result. So everything that ends up over here, this is just going off into the bit bucket, and I won't care about it. Now, even though machines may double the size of the result, for our purposes and our homeworks, we're going to stick to the original data size we were using on the machine, just to keep everything compressed. All right, so 1 plus nothing is 1. Zeros all the way, 0, 1. 1 plus 1 is 2. That's a 0, carry the 1. 1 plus 1 plus 1 is 3. 1, carry the 1. 1 plus 1 is 2. That's a 0, carry the 1. 3 ones, 1, carry the 1. 3 ones, 1, carry the 1. And in the end, we would get a 1, 0 here. But both of those bits are thrown off to the bit bucket. So 29 times 89 is going to give us whatever this bit pattern here is. Now, we could figure out what that is, but I don't care what it is. The important part here, because it's too big, we've overflowed, and so we're going to have some value that doesn't appear to make sense. And it's going to have wrapped around and around our representational space at least several times. So it's going to do us no great benefit to try to figure out what it means and why. What's more important is we understand that what we have done is just raw mechanics with no thoughtfulness whatsoever, as our computers will do. If you remember that comparison in a very early lecture about the ant and the swarm of ants, and that computers are really like that little transistor and then lots of them put together in parallel, and so they seem to do bigger, fancier things, but they really aren't bigger, fancier things, or they aren't so fancy that we have to be astounded. That's what we're looking at here. Each of these three types of arithmetic are very simple, and we can perform them mindlessly and be confident that our results are good. Now, for the multiplication, you may be a little more concerned personally about the issue of sign. Like, what if I took a negative number and multiply it by a positive number, or two negative numbers, right, or something like that. And so I'm not going to record that in this video, and I'll leave it up to you as an exercise, but pick some small numbers. Use a 6-bit representation, because that's relatively small, and multiply the numbers 5 and 6. Right? That'll give you 30, and 30 fits in 6 bits. It fits in 5 bits. But because it fits in 5 bits, the high order bit is guaranteed to be a 0 when you do positive 5 times positive 6. But then you can come up with the bit strings for negative 5 and negative 6. You can try all the multiplications. 5 times 6, negative 5 times 6. 5 times negative 6, and negative 5 times negative 6. And you will see that you always get the appropriate magnitude and sign answer, positive or negative 30.